Okay, so welcome everyone to the Applied and Computational Maths seminar. Yeah, great to see so many people in person and people online as well. So yeah, continuing the trend of having good hybrid turnouts to do things, but a great pleasure to have today Richard Porter from University of Bristol. So Richard's a professor in applied mathematics there and has got some related problems to waves and free surfaces and metamaterials, and this is a kind of nice combination of those two things. So yeah, excellent, and yeah, welcome, and away you go.
Okay, thank you very much. Thanks for the invite, and thanks to everybody for coming. This is the first in-person seminar I've given for a long time. Yeah, no, it is. I was going to say I've given a conference seminar, but I haven't recently. So yeah, so it's good to be doing this in real life rather than on Zoom. So my talk today is about water waves and about the interaction of what I call water wave metamaterials with the propagation of water waves. So metamaterials are defined to be something which have a micro scale with respect to the length scale of the water waves. And really, the whole talk is about the strange effects that you can manifest on water waves by placing a metamaterial in the ocean. So these are non-intuitive effects that are quite interesting and exciting, and then have other applications that can be developed from that. So this is work that I've done with over a period of time with a number of different co-authors. Christos was my PhD student. Henry is at Imperial College. He's a PhD student, but I'm working with him on something I'm not going to mention here. Jin's a recent postdoc of mine supported by the UPSRC, and Siming is at Plymouth, and Hui Liang is at Singapore. So they've all contributed in various ways. So this is the brief outline of my talk. I'm going to start with an introduction to water waves. So starting with the general description of water waves in fluid dynamics, and then talking about the simplifications that I want to make, and perhaps the reasons why I want to make those simplifications. Okay, and then I'm going to take you through a story of what metamaterials can do for you, and I'm just going to use as an example invisibility cloaking, which is kind of like the hottest topic that metamaterials was used for back in the day. And that gives us an idea of how to introduce what's called anisotropy to wave propagation. And then the latter half of the talk is about my interpretation of how you actually produce this anisotropy and wave propagation by using various metamaterial devices, and my own speciality is what I call bathymetric plate arrays. Okay, and towards the end I'll show you some examples of things you can do using this setup. Okay, so this is the full set of equations describing the motion of a fluid with a free surface. This is my sketch. This is a three-dimensional sketch with Z pointing upwards. From the mean free surface, I have some variable bathymetry described by H, and I have a free surface elevation zeta. And so I've got mass, momentum, so incompressibility condition, Navier-Stokes equations, not the Navier-Stokes, the Euler equations, the inviscid equations, dealing with only with inviscid fluids. I have no normal flow on solid boundaries, and then I have a moving boundary condition. And of course, this is a very difficult problem. I don't want to work with something as difficult as this. I want to simplify things, and in particular, you'll see that there are all kinds of difficulties. So I've got a moving boundary value problem here, so this is difficult. I have a nonlinear term here, so that's difficult. But actually, the thing that I want to pick out in this particular problem is this term here. So this is what makes water waves different in terms of looking at it in the view of metamaterials than other physical sciences such as acoustics, elasticity, electromagnetics. And the reason is that gravity has got a special direction down. Okay, so wave propagation, as we know, happens in the horizontal plane. Waves are surface waves. They only live on the surface, and they do something special in the depth, so they decay exponentially into the depth. So one of the coordinates is acts in a different way to the other two directions, and that's my main difficulty. Going back to the original difficulties, I can get rid of the nonlinearity by using the linearization assumption for water waves, so that I have small amplitudes. And then I can do two other things to simplify my life. I can either decide that the fluid is, I'm thinking of ocean waves here, that it's on a big enough scale that I'm going to assume that there's no vorticity and that I have an irrotational flow, and I can introduce a velocity potential. And that will take me down one route where I can start thinking about the full three-dimensional problem. Or I can do another simplification, which is what I call shallow water theory, where I assume that there's a contrast in length scales. I have long waves compared to the depth. And in that particular situation, I can assume that the velocity profile is effectively two-dimensional. So the fluid is moving in the horizontal plane with very little accelerational velocity in the vertical direction. So that's my shallow water assumption. I'm going to use both descriptions. So this is the first one. This is what happens when you introduce a velocity potential. You end up with these three-dimensional equations. So your mass equation reduces to Laplace's equation in the fluid. These are your Neumann conditions on fixed surfaces representing no flow. And then the free surface represents the dynamic and kinematic conditions. So this is where momentum comes in, and it's driven by gravity. So I end up with a mixed condition on the free surface. So if I want to solve full depth-dependent three-dimensional flows, these are the equations that I want to think about using, solving Laplace's equation in 3 dimensions. I can make some other assumptions here. So I can, this is a time-dependent problem, it's linear, so immediately I can take out the time dependence through a transform into the frequency domain. So I don't have to think about time dependence, it can just be represented by a frequency component. And secondly, I can, if I assume that I have uniform depth dependence, so whatever I have in my ocean is flat, whatever I have in my ocean, if it protrudes uniformly through the depth, like a circular cylinder, for example, then I can factorize out the depth dependence through a Cauchy term here, and that leaves me with a two-dimensional equation. And that's just a two-dimensional standard membrane or wave equation. Okay, so the ultimate simplification is that I've got down to this two-dimensional equation. If I assume that I have a flat ocean with things protruding uniformly through the depth. Okay, so that's my ultimate simplification in this particular case. Then I have shallow water theory, and I can use that as well. Shallow water theory assumes that I have long waves, shallow water, okay, in which case I can develop some machinery. This is just a very sort of brief explanation as to what goes on here. I can assume that the pressure is hydrostatic, it's just driven by the surface elevation. Okay, and then these are my mass and momentum equations. So these are linearized under these situations. Q is the horizontal depth average flux vector. So Q represents the transport of fluid in the horizontal, two-dimensional horizontal directions. And then I can eliminate between these two, and this is my linear shallow water equation. I mean, you can add things on top of this to make this into a non-linear shallow water equation. There are extra things that you can do to make this more difficult. But again, this is my simplest thing that I can represent here. And the advantage with using this over the previous representation, I have to pay a penalty because I need long waves and shallow water. The particular advantage of this is that it's two-dimensional. These are the two-dimensional gradients and divergence operators. It's two-dimensional, but I'm now allowing the depth to vary. So the depth can still be a variable function here. Okay, so why am I looking at these two particular things? So either an equation for phi, a three-dimensional equation, which can be reduced to 2D on the basis that things are uniform, or this two-dimensional equation for eta. Why not just solve the full three-dimensional equations? And the reason is that I want to appeal to things that people have done in other areas of science using metamaterials. Again, I want to apply those to a water wave setting. Okay, and so the typical method that's used in these other areas, going back to the early 2000s, was this method of coordinate transformation, or transformation media technique, it was called. And it's a very, very straightforward method to use. And so I'll just describe how it gets used and then how it fits in with what I've just said before with water waves. So imagine now I'm looking down upon the fluid from above. Okay, and this is a fluid of constant depth h naught on the left-hand side. B is just some virtual cylinder that I've just drawn into the flow here. And these horizontal lines just represent coordinate lines. Okay, so these are just y equals a constant, different constants. And so on the left-hand side, I've got nothing, there's no obstacle in the way. This is just a virtual line that I've drawn here. I've got a constant depth. So this is my equation. Whether or not I look at this under shallow water theory or potential theory, this is the equation which describes the motion of the waves on top of that fluid. And the solution is straightforward. It's just a wave traveling from left to right. I mean, there's a wave from right to left as well. I'm just looking at something coming from a plane wave coming in from the left-hand side and just moving across from left to right on that picture. And it has a wave number k naught and the wave numbers associated to the wave frequency, and it depends upon the depth. The wave speed is C here is the square root of GH, which is the shallow water wave speed. Okay, and what you do under this method is you decide to map the left-hand diagram to the right-hand diagram. And the mapping that I've shown here imagines that the origin on the left-hand side is blown up to give me a circle of radius A on the right-hand side, whilst the radius B is maintained at radius B. So you've taken inside this circle here and you've moved it into this annular region under a mapping. And you can decide what that mapping should be. It can just simply be a linear mapping, or it could be a non-linear mapping. Okay, and under that mapping, of course, your coordinates change. Okay, so you end up changing the equation and the boundary conditions and everything that you've set up in the left-hand side. Okay, so under the mapping, your original wave equation changes to this wave equation here, and the key thing is that you can make it look like another shallow water equation. Now, under the mapping, you can preserve the equation. That is to say that this picture here can be interpreted as a water wave scattering problem. But in doing so, I have to introduce two things that weren't in my original problem. The first thing I need to introduce is this tensor H, okay, which encodes something to do with the depth. And it tells me that I need my depth to be different for waves traveling in the radial direction and waves traveling in the angular direction. Not just different in the entire annular region, it depends upon the radius as well. So I have to have spatially varying anisotropy in the depth. So waves need to feel different depths when they're traveling in different directions at different points in space. So that's one of the problems. And the second problem is that this mapping also introduces a factor here. Omega is fixed by me. So in order to make sense of this and interpret this as a real physical problem, what it means is that I need gravity to be spatially dependent as well. So I somehow need to be able to, in order to realize this cloak, this now becomes my cloaking region, I need to invent an anisotropic spatially varying depth and a spatially varying gravity. I'm not going to talk about how you do gravity, but you can do that. Right. So what does this look like? So here is a circular cylinder. This is exactly the picture that I've just shown here. On the far left-hand side, we have waves coming in from the left, hitting a circular cylinder. That circular cylinder doesn't have a cloak around it of the design that I've just described. The waves just hit the circular cylinder over a flat depth h naught, and they get diffracted. Okay, so that's the pattern that you see there. If I was to introduce a perfect cloak, the one that I've just described, okay, with the HRR, the H theta theta, and the kappa, as prescribed by the mapping, and I draw what the solution looks like, this is the solution I get. So this is what I call cloaking. The waves come in and they just sweep around the cylinder and move off. Okay? And cloaking means that if you're an observer somewhere in the far field, all you see is the waves coming past as though the cylinder weren't there. Okay? If you ignore this problem with gravity and you just do the the depth being anisotropic, and ignore the gravity and use a particular non-linear map. So there's a way that you can try and get around the problem of varying gravity. And this it was done by a couple of authors in 2015. Then you can produce this as your cloaking solution. And you can see perhaps that there's a little bit of scattering in here, but just a very, very small amount. So this is a near perfect cloak. So these people, what I want to move on is how do you actually build one of these cloaks? How do you actually build a depth which is spatially varying and anisotropic? These people didn't actually address that problem. They didn't say exactly how they were going to do this. They just did a different type of map which got rid of the problem of gravity. Meanwhile, I was working on this problem, and I was doing it in a rather naive sense because I didn't at that time know how I could build one of these anisotropic depths. So I was just looking at normal depth variations, and I was just trying to use different types of depth variations under some kind of optimization routine to work out if I could get close to perfect trapping. I worked with a guy called Nick Newman, and together over a period of time we produced some examples of varying bathymetry. So here you can see this is sort of a cutaway diagram of a three-dimensional picture in which I've got a vertical circular cylinder, and now you can imagine that this is the varying bottom here. And these were different types of realizations which produced practically no scattering. The reason I call this a poor man's cloak is that whilst these examples up here work for all incident wave frequencies, so it doesn't matter what the signal is, it always gets swept around the cylinder. This one was just targeted at a single wave frequency, so it only worked at one particular frequency. Okay, so how do you build one of these devices? So this is one way that you can do it. Remember, the way that you need to do it is you need to somehow introduce some kind of tensor in place of the depth in the shallow water equations, and that tensor needs to be diagonal, and it needs to be spatially varying. And so one thing that you can do is use a method of homogenization. And so in 2008, a series of authors looked at this particular problem in which they took an array of very, very small vertical posts which were uniform through the depth. Because they're uniform through the depth, I can use my potential theory. That's exact now. Okay? And then using the contrasts in scales between the length scale of the incident wave and the length scale of the posts, and then using a homogenization method, you can actually transform this equation into this equation under homogenization. So you can introduce a tensor, okay, and that tensor turns out to be symmetric as you want. If you use a symmetric post, you can turn off the off-diagonal terms here. This is just, I don't really want to go into a description of this, but this is a microscale problem you need to be able to solve in order to be able to determine what these coefficients should be in this tensor. But you can make these spatially varying by changing the size of this vertical post. And that's what you see in the experiments and the simulations that they did. Okay, so there's some spatial varying sizes of posts as you go from the inside of the ring to the outside of the ring. So this was their attempt at producing a cloak. Okay, and that's all well and good, apart from the fact that they missed out this problem to do with gravity that I mentioned before. So they weren't able to deal with the other issue of how do you vary the other parameter, which wasn't the depth tensor. So this is my own work, where my own work comes in, and I envisaged creating anisotropy in a different way. So I imagine something rather like I call it a toast rack, right? So you've got something which is formed by some plates, okay, in one direction coming out from the bottom, just a series of thin plates. And the idea is the following, right? If I have waves traveling, so here are my plates like this. If I have waves traveling in this direction over the top of the plates are very, very close together, and the wave just feels the top of these plates. It just imagines that the depth is like formed by the top of this toast rack. If I turn the plate array round by 90 degrees, and now have my waves traveling, the depth that they feel is the depth running all the way down to the bottom of the toast rack. Okay, so what I'm able to do is I'm able to make the waves feel different depths when they're traveling in different directions. Okay, and that's the anisotropy that I want. Okay, so you can do this in different ways, but it's appealing to do this under shallow water because things are very explicit with shallow water. So again, we can develop machinery under shallow water to see exactly how these depths affect that wave propagation. And this is basically why I introduced it earlier on. So I can do the same thing as before. I can assume that the pressure is hydrostatic. Okay, then I can think about the depth averaged horizontal flux. And now this is really easy to think about because the flux in this direction is just the velocity multiplied by the depth in this direction, which is h minus. Okay, and the flux that I can allow in this direction here is not just h plus, but the bit between the plates as well. So it's h plus this 1 minus this theta gives me the ratio telling me how thick these are. 1 minus theta times h plus minus h minus. And this gives me the volume flux moving in this direction. I mean, there's different ways that you can set this up. You can do this formally using homogenization. This is rather more heuristic. And then these are my depth integrated mass and momentum. The only difference to before is that I've got this tensor in because I've got this anisotropy in the flux. And I put these together and I have this what I call an effective medium equation. So this looks like my linear shallow water equation that I had before. The only difference is now is that I've got this diagonal tensor and I can control, I can make the depth feel different for waves traveling in one direction and a different direction. So this is a proposed way of producing anisotropies. I'm trying to persuade Nick Newman to actually do computations of that invisibility cloak using the prescription based upon these plate arrays, because he's got some boundary element code that can do it exactly. This is just shallow water theory, so it's just an approximation. What do I want to say about this? So this was my own theory, and there are other people that had used these plate arrays as well. There's a group in France, Agnès Morel and others have been using a similar type of idea, well, exactly the same idea. The only difference being that their plate array, although this looks very, very close, this is what I'm thinking about here, they were imagining that their plates could be widely separated as well. And so I have some agreement with them. So the blue curve is the case that I'm thinking about. I've got these plates very, very close together so that the waves running over the top just feel the tops of these. The fluid flow doesn't have a chance to dip into each of these cavities here. Okay, and so my predictions of this green line will coincide with this green line and with this horizontal coordinate. So they match up with other people's simulations. So mine is explicit, and these are numerical computations that have to be done. Right. So so what can you do with these plate arrays? You can build one of these invisibility cloaking devices if you want to. But I wanted to look at other more fundamental types of problems that you might want to look at. So I'm now going to imagine a problem in which I send in waves. This is a scattering problem. I send in waves from the left. Okay, so this is this is an infinite domain divided into two semi-infinite domains along x equals 0. So you imagine oblique waves coming in from the left-hand side and meeting this plate array bathymetry on the right-hand side, and it goes on forever on the right-hand side. Okay, and I can define a depth h naught on the left-hand side, and then I can define the height of the plates and the depth of the plates to be h plus and h minus. They don't have to coincide with h naught anymore. And I can define the angle through which these are rotated, okay, as well as the thickness of these plates. I've drawn them as 0 thickness here because that's easier to think about, and it gives you the greatest amount of anisotropy. Okay, so I'm going to think about a scattering problem. So on the left-hand side, I've got my normal shallow water equation with h naught, and I can write down my solution very easily. There's a wave coming in from the right and a reflected wave coming in, going back out to the left. I don't know what just happened there.
I think it might have reconnected. Want to share your screen again? Yeah, because it's not coming through.
Return to meeting.
Yeah, and then at the bottom, do you have the option to share? Yeah, just try that again. And now click behind. Yeah. Oh. It doesn't seem to be coming through in here, does it?
It might be a problem with my internet connection.
Yeah.
Because I'm connected.
Yeah. Maybe try sharing the application. Or I think when you close Zoom, it closes the.
Shall I reopen Zoom again?
If you go on meetings on the bottom, the clock at the bottom. Yeah, you should try and reconnect to the call.
See, I'm on there.
No, this is just this laptop. You're not connected to this Zoom call now. Let's try and. Okay. Is it connected to Eduroam? Yeah.
It looks like I'm having a problem with it.
Yeah. Well. Maybe some maintenance. If not, we can just continue and use this stream as the only recorded stream, and we'll try and patch up. Yeah.
Are you on Wi-Fi?
Yeah, I think so. I'm connected to the call, so yeah.
For some reason or other, it's just my internet connection's just completely flaked.
Yeah. Should we just go back to the talk and continue with this stream?
Yeah, if you want.
Unless you want to do more. Take too much time away from the talk. Oh well. Hopefully everyone online can see enough of the screen. Is that just not visible on the...
It might be.
Could it be better placed somehow?
I don't know. It doesn't matter.
Should we just try from there? Might be some works going on. Sorry about that.
Yeah. Okay. Yeah. So I'm looking at this particular scattering problem to see if I can determine what the reflected waves are. So on the left-hand side, I've got I can write down my solution very easily. Okay, and I've got the important thing here is I've got oblique waves coming in, angle theta naught. And I can think of a simple situation in which I can get some very simple solutions. So for example, if I raise this bed up to here, okay, and then I've got my plates aligned at this angle, and I send in my wave at exactly the same angle as the plates, okay, then the waves are just going to pass straight through. They're going to slide straight through, and I'm going to get no reflection and total transmission. Okay, so that's a special case. I can also drop the H minus down to the level of H naught, so I can still have this pit, but I can drop the level down to, and then if I've got waves coming in this direction, it's like riding a bike over a cattle grid, right? You don't drop down the slots, you just ride over the top, and again, you'll just get perfect transmission. So there are these kind of special cases. Okay, on the right-hand side, I can use this tensor that I've just developed, this H, that's this H here, And then I've also developed this thing whereby I can twist the whole plate array round by this angle delta, and that just encoded in a rotation matrix. Because I've made another change of variables to move things around here. Okay, so delta is something I can change. I can work out the solution. There's a lot of, this is all analytic. The only reason I'm showing you this is that you can just work out the solution exactly. And you can work out your R and T, and it looks like this. So Q is some mess to do with the different depths and certain other parameters, but you don't need to worry about that. The interesting thing here is that I can see when R is equal to 0, it's when Q is cos theta naught, right? So whenever this is cos theta naught, I get 0 reflection and total transmission. Okay, and I'll just point out what actually happens in practice is that you can actually find certain parameter sets in which this Q can always be equal to cos theta naught, irrespective of what theta naught is. Right? So that is to say, you can get total transmission, 0 reflection, for all angles of incidence, for all wave numbers. Okay, and this is what some of these pictures look like. Okay, so here I've got a Gaussian beam coming in. A Gaussian beam is a weighted integral over all angles theta naught, but that doesn't matter because it's this. I get total transmission for all angles theta naught. And I've got a beam coming in here, hitting a finite slab of this metamaterial and then being propagated onwards. Okay, so here it comes in. This is when theta naught equals 0, or the center of the Gaussian beam is aligned with the x-axis. And then it comes back out again. And what you can see is this refraction happening over the bed. It's the waves are being refracted. And in fact, they're being, in certain circumstances, being negatively refracted. So this is a big thing in metamaterials. Can you do odd things with waves? Can you produce negative refraction? So here's a perfect example. The wave comes in, hits the material, bends back, and then goes onwards. Okay, and you can actually work out when this happens by looking at the group velocity, which propagates the energy. And so, for example, in this case here, you can have positive angles of incidence, negative angles of transmission. And that would be a wave coming in this way and then bending back that way. Okay, so it's very neat when you're using shallow water theory because everything is explicit and you can see exactly how things are going to work. So these are the types of pictures that you can get. That's shallow water theory. So the question is how good is shallow water theory? It's made upon this assumption that you have very long waves compared to the shallow water. So we've also done calculations in using the full three-dimensional potential theory. That's a lot more difficult to solve because you're working with one extra dimension now. But we're able to get both qualitative and quantitative agreement with results. If the wave number is very, very small, that's long waves, then you get very good qualitative agreement, and you still get good quantitative agreement for higher values of the wave number or for shorter wavelengths. So again, this is just demonstrating pictures like the ones that we've just seen before, showing that you can get negative refraction, waves coming in, being refracted backwards and then propagating onwards. The difference between these three plots is that the arrays that are coming from the bottom are going up very, very close to the surface, a bit further down from the surface, and then further away from the surface. So the influence of the bathymetry on the surface waves is kind of dependent upon how close I am to the surface. So you get the most refraction when your plate array is really close to the surface and affecting the waves more. I'll just mention this because this is all to do with plate arrays that don't protrude all the way through the depth. If the plate array protrudes all the way through the depth, then actually your life becomes a lot easier, because then you don't have to use shallow water theory anymore. You can use full potential theory, and you can take out this cost dependence and give yourself a two-dimensional problem. Okay? And in fact, this piece of work preceded the stuff that I've just shown you about with the bathymetric plate arrays. So this again is a similar situation showing negative refraction. The reason I want to show you this is because this predicts that if I had some kind of waveguide, a channel connected to another channel through a bend, and I put plates like this in this bend at negative the angle, say so waves coming in at 45 degrees then bent back at 45 degrees, and then propagating at 45 degrees. This situation here predicts that you get total transmission of all wavelengths. And that's not a shallow water result, that's for all frequencies. No wave energy will get reflected back, it will all get transmitted through this bend. The reason that's interesting is there's this guy, Vincent Pagneux, in Paris, or Le Mans University, and he's doing experiments and has shown me results that confirms this experimentally, or doesn't confirm it exactly, but shows very, very good agreement. It shows that you get high amounts of transmission through this bend. Okay, so I'm getting close to where I want to be. I'm just going to show you some more examples of what you can do with this metamaterial device to manipulate waves in some bespoke manner. This is very similar to the invisibility cloaking problem that I told you about right at the beginning. It's based upon the same idea that you use a mapping to take you from a problem where you know what the solution is into another problem in which you want something to happen. And so I can imagine on the left-hand side waves traveling down a straight channel with a uniform depth. This is me looking down on that channel, waves coming in like this. And then I imagine that I get this straight channel and I just bend it over my knee. Okay, so here's me bending the channel. In order to bend the channel, mathematically, I have to do a mapping. Okay, so this is a mapping from the left-hand side to the right-hand side. My left-hand picture, I've got standard shallow water equation. I do the mapping. Actually, I've written it out explicitly here. This maps you from left to right. Under the mapping, the shallow water equation maps to this equation here, in which gravity doesn't vary, which was a problem before, okay, but only the depth varies. And this gives me a prescription as to what the depth should be. Explicitly, it tells me that the depth needs to go down like 1/r squared for waves traveling in the radial direction, and like r squared for waves traveling in the angular direction. So again, you could build one of these things. You could put in a crisscross of plates to mimic these two depths, okay? And the idea would be that you could perfectly transmit, okay? Because in the left-hand diagram, the waves just travel from left to right. So if you do the mapping right and you build this thing in the right way, you're going to get perfect transmission around the bend. Okay, so here's a diagram showing what happens when you put in one of these metamaterials. This is just a computed solution. There's a bit of a problem because you get an impedance mismatch at this boundary and this boundary. It's a very, very small impedance mismatch, so you get basically perfect transmission. Okay, if I didn't have an anisotropic bed, if I just had a flat bed, this would just be a mess. Waves would just be reflected back. Okay, this is like blowing sound down a pipe, right? You get some back reflection back from the bend if you didn't have this device allowing perfect transmission. Okay, so the final thing to look at is the effect of these bathymetric plate arrays when they extend uniformly throughout the depth. So here I'm back to using phi again, and I can use it for all frequencies. I don't have to use shallow water theory. And instead of having sort of a semi-infinite domain or a strip or a slab of this bathymetric material, I've now arranged it in a circle. I'm using a circle because I can do semi-analytic things with circles. So this is what I'm imagining. I've submerged this thing, as is suggested on the right-hand diagram, this sort of toast rack through the water. And now the fluid can flow in between each of these surfaces. Okay, and to me, this is interesting. That's the reason I looked at it, because this is clearly an anisotropic cylinder in terms of its scattering properties. That is to say, if I send in waves from this direction, the wave just slides straight through the cylinder. I get no scattering at all. Okay? Whereas, of course, if I send in waves from this direction, something's going to happen. Right? So, for me, this was interesting because I thought, oh, well, this might be an interesting device. It's something you could imagine being tunable. You could twist it around according to different wave conditions to do different things on different days. Okay. Okay, so there's a method of looking at this, and this is what happens. Just a sequence of results here. This is different from using media transformation to design something specifically to do something like transmit perfectly or cloak. This was me just playing around with something and seeing what happens if you use this thing. Okay, so I didn't know what was going to happen, but here's my cylinder here. I've got waves coming in, now long waves coming in from the left-hand corner at 45 degrees, and they're now interacting with this plate array cylinder. And what you can see is, this is the frequency increasing, is that you're promoting this resonance inside the cylinder. So the surface is pumping up and down quite hard. And it gets worse, or more violent. And eventually, actually, this is quite serious, because the whole solution now fails to converge. Now, the reason that you can think about this, or one way of thinking about this, is imagining that each of these strips that I've just drawn here, each of these strips is essentially like a string. It satisfies a one-dimensional wave equation. Okay, so it's like an organ pipe or a string, and it has natural frequencies of vibration. So this is like a series of, it's like a harp, if you like, right? All of these strings are of different lengths. And the problem is as soon as you introduce a frequency which is high enough, you're going to excite a resonance in one of those organ pipes or one of those strings. So provided your frequency is low enough, you just see some excitation on these strings or in these channels. If you go above a critical value, suddenly you excite one of these resonances. Once you excite one of these resonances, you just get complete rubbish. Okay, so there's some comparison here. You say, well, does this model work? Well, we've compared it with different CFD models. We've used commercial software, and we've used our own bespoke boundary element software to confirm that if you take it, we're using a homogenized system here, right? So it's an approximation. We're comparing it now with a discrete system of, say, 20 plates and looking for agreement. So that works out quite well. I think so. Two more things to say is that if you take multiple, there's interesting things happen if you take more than one of these cylinders. And we've got lots of work going on different types of things we can do. But here's just two cylinders placed side by side with waves coming in from the bottom. And they're tuned at a frequency low enough that we don't get this rubbish happening, where you hit one of the resonances in the organ pipe. And then you imagine now that you can turn these cylinders round. Okay? What happens is that this energy that gets resonating inside these cylinders, it represents some kind of slow wave propagation through the cylinder, and then it fires out wave energy normal to this direction here. So what you can end up doing is focusing waves on a certain point, or indeed defocusing waves away from a point. So if you had a harbour entrance here, you could use these elements as a way of defocusing, moving wave energy away from a point if you wanted to do that. Okay, and then the last thing to do, to say, is going back to this problem that I had here with this non-convergence. I mean, I'm not very sophisticated. I mean, I'm trying to work out how to get around this problem mathematically. There's a problem with the matching of the boundary conditions here, which is quite a tricky one to sort out, I think. But in the interim, what we decided to do was just to add some damping to the problem. Because there's resonance here, there's something blowing up to infinity, that's causing us problems. So we just added some damping into the inside of the cylinder to see what would happen. Okay, and again, we didn't know what the results would look like. And here are a series of results which are relatively meaningless to me. Oh no, it's all coming back now. So you can imagine now that this represents a wave energy converter, something that harnesses wave energy, the damping. Imagine the damping that I've applied to this problem is useful damping. It's taking energy out of the waves in a useful way. It's at the moment it's artificial, because I've just applied some kind of some heuristic sort of damping to the problem. But imagine that this was a physical mechanism behind this damping here. These lines show me what's called the capture factor, or normalized capture factor, which is a measure of how good that wave energy device would be. Now, a normal wave energy device, okay, if I take a circular cylinder and attach it to a piston, and it just bobs up and down in the ocean, and I take energy out of that. The maximum energy that I can take out from that on this scale here is 1. Okay. If I make the cylinder bob up and down and move from side to side, that's two different modes of motion. I can increase this to 3. Okay, but that's the most you can. 3 is the most you can get out of a traditional wave energy converter under rigid body motion. And so what we're showing here, and these are just preliminary results actually. I don't know why I'm not showing better results than this. You can get, I think this scale can go up to about 16, right? So using a non-traditional, that is to say, this microstructure device, it's possible to use these types of things as a wave energy extraction. That's what Jin Wang, my PhD student, is working on with me now, is trying to do exactly what I suggested, put in proper physical mechanisms for wave energy absorption as a method of trying to realize one of these as a device. Okay, and so I suppose I should summarize. Yeah, so the first two are fairly self-explanatory. Water waves offer a nice way of visualizing effects in experiments. I think that's really nice to be able to do experiments on these types of problems, and actually a lot of these things happen in acoustics, metamaterial effects, and it's very, very difficult to visualize them, but metamaterials are really nice to visualize under water waves. Then wave energy converters, and then the thing that I'm interested in at the moment is talking about homogenization. That's how I model all of these things through homogenization. Talked about homogenization in the bulk, and it's the same plate arrays that occupy the volume. We put them on the base of the fluid, and the next thing to think about is what happens if you put these things on the surface of the fluid, and say, well, how can we manipulate waves by having active devices, floating masses on the surface? And that's really interesting because they are truly active. You can actually put springs and dampers on them and control waves in a non-passive way. So that's something I'm going to be working on in the future. Anyway, thank you for your time and attention. Thank you.
Yeah, thanks a lot, Richard. That was really excellent. So, yeah, have we got any questions from audience, or we can also take some from online as well. If anyone would like to ask questions online, you can just put them in the chat.
Quick question. Is a group in Manchester also working on cloaking and metamaterials in wind farm and then in other hubs?
Yes, yes,
so how is your work connected to them? Because you said you're using things from other people. I mean, from
yeah, I mean, there's a lot of ideas that are shared between.
But they also manufacture things, and they also have to.
Yeah, I mean, Will works a lot on kind of acoustics. He worked either on underwater acoustics with like industrial partners like Thales.
Yes.
And but he also works with Dyson on like noise control and broadband sound absorption. Yes. And we're all stealing ideas off each other. So he's not working on water wave problems.
No, it's not water. I realize that you're
yeah, there's a group at Imperial. Richard Cresta, Sebastian Gano, and actually they like these cylinders, and they've stolen the cylinders and they're using them for other things. They're really interested in the cylinder things. So yeah, it's just being passed around, and everybody's just sort of nibbling at it as it gets passed around.
Yeah, it's interesting to see these actually produced
in
manufacturing. They're not just ideas; they're real things.
Yeah, I mean, I haven't actually seen any of these. I don't work closely enough to these other application areas to see these things being developed.
What direction to go?
Yeah.
Okay.
Anyone else from our audience here? Serena?
Yes, I've been collaboration. So you have any plans for the way what are the applications you're envisioning for that?
Yeah, the wave energy stuff that my postdoc's working with me on is a range of different problems. So one One is taking this cylinder with these plates and putting paddles at the center of the cylinder. So, as I say, we've added damping artificially to the cylinder and seen that there's a lot of power come out, but you need something which represents something that you would build physically. So we've imagined that that might be paddles in one instance, and that works basically just as well. It doesn't really matter where the damping happens inside. Turns out it doesn't matter where the damping happens, as long as you've got some damping somewhere inside the cylinder, it will take out the power that you want, the power that's available. So that's one conclusion that we've drawn. But we're also looking at problems where the cylinder doesn't go all the way. At the moment, the stuff I showed you here was a cylinder going all the way through the depth, because that's an easy problem to do, because it's two-dimensional. But a cylinder that doesn't go all the way through the depth is then harder, it's three-dimensional. But there we're imagining something slightly different, where instead of just having one plate array, we've got two plate arrays overlapping. Right, so we've kind of got like a barbecue grill sort of thing going on. And then you can put masses in between each of these slots. And so basically you can have a huge array of little floats arranged on sort of like on a crisscross pattern, each attached to a spring and a damper. And that's another way of looking at this problem, trying to take out power using a microstructure, and that works very well as well. So, and then we have other ideas about what to do as well. Sorry,
internal gravity waves.
Internal gravity waves.
You can have both sides, right? You can get energy from both sides.
So with a two-layer fluid type of thing.
Well, the density is changing practically. So in reality, you have the changing density, right?
Well, I mean, it wouldn't change in a normal situation. The density of water on the scale that we're talking about here would be fairly constant. I mean, I'm not thinking about anything with any kind of salinity.
What length scale are we talking about?
For a wave energy device.
Yeah, so that you can still interact with internal gravity.
Yeah, I mean, you could do. You'd have to know that that was a problem that was out, that you wanted something with a thermocline, you know, with a density or thermal stratification of density. If that was if that really was something that you needed to sort. I don't think it's, for me, it doesn't feel like a leading order problem. It feels like a second order problem that you'd add on.
Yeah. The last figure that you showed.
Yeah.
So you can look at that as a quality.
It's like, yeah, this is essentially, yeah, it's like a quality. Yes, exactly that. Yeah.
How's the thickness of the things coming from
I mean, it makes a small difference. I mean, we've assumed in our model that they're infinitely thin because we're mathematicians, but you know, in reality, so this comparison here, this one here was that the thickness is 20% of the total distance between. So if it's a meter between each plate, these were 20 centimeters wide, these plates, and then you get. This is the kind of agreement that you get between the two. So this would be an infinitely thin, infinitesimal spacing, and this is real spacing of 1 meter with 20 centimeter thickness plates. So it's pretty close, right?
Yeah, but if it's infinitely thin, then H minus basically would be equal to H plus, right?
So infinitely thin, but these are coming all the way through the depth now. These are vertical plates coming all the way through the depth.
So you would have a step.
This is not the depth dependent. This is not the depth dependent problem. This is one.
Okay. Yeah. Otherwise, you'd have reflection.
Of course, yes. Of course. course. No. So this is one where I've taken plates and I've arranged them vertically, dropped them all the way down to the bottom.
So in the depth dependency, if you take it relatively dependent, you see actually that reflection.
Yes, of course. Yes.
Yeah, everyone thought it's probably in a similar thread, just about, you've done active coupling where you say you may move things in the problem, you might have some form of dissipation that obviously could come as well from thickness and things. What about like the natural coupling? Say if these plates were elastic in some way and they had their own frequency of oscillation that was quite different to the frequencies, could it, it sounds on the surface like it would be purely distant, but could there be some funky areas where it helps the resonance effect?
No, that's certainly a good idea. Yeah, or is it,
that would be tunable as well.
Exactly. So I guess you get all kinds of interesting things happen when you have coupling of two different mechanical systems which have two different resonances. So yeah, you might see very interesting things if you try to do that. Again, you'd have to ask yourself, do I want to do this? It's a problem that can be done, but then you have to have a reason to do it. Either it's an engineering problem that you decide you have to face, or you say there's something attractive about doing that makes me want to look at this problem.
I guess the only attraction would be if you could boost the resonance
Yeah,
beyond if it was just the best rigid material. In inverted commas, you do that.
You're right, of course, yeah. If you don't try, you won't know. Yeah, so there might be something.
Excellent. So
Okay.
yeah, I think that's everything. Yeah, excellent. So yeah, let's thank Richard again.
Thank you.